Hi everyone. Hope everybody's doing well. Today we're going to talk real quickly about doing an analysis of variance and do an example in Excel and work through that. so analysis of variance and is typically referred to as ANOVA, or it's used when testing the means between two or more groups simultaneously. So we've talked about t-test already, which looks at the means. Compares the means between two groups, two individual assessments, two individual groups, however you want to look at it. ANOVA just includes more than two, essentially, and it sees if the group means significantly differ on a particular score of a variable. So if you want to look at the difference between parolees and probationers on recidivism, you can look at individuals who were on neither and include that into the group, right? And see how they recidivate. Like if they fulfilled their full sentence in prison and got out and released free into the community without being placed on parole. To do this, it's just the addition of an additional group. So to do this, you incorporate an F test. So before it was a T test. This one, with adding more than two groups, it's an F test, all right, named after Fisher. But this is kind of the flow chart. Talked about this before. Looking at a flow chart that comes out of your textbook on how you want to assess, the steps that you want to take to see that you're conducting the appropriate test, right? So here, if we're examining the relationship between variables and all this type of stuff, how many groups are you dealing with? Well, two groups. We did a t-test for independent samples, but we got more than two groups, so we want to look at simple analysis of variance, or ANOVA, a simple ANOVA, right? You have repeated measures. You can also do repeated measures ANOVA as well. We did that for dependent samples, a t-test for dependent samples last time. So today we're just going to really focus on the idea of simple analysis or variance, or simple ANOVA, right? So a simple ANOVA, also called a one-way analysis of variance, used when one factor or one treatment variable is being explored, and this factor has more than two levels. So like I mentioned before, more than two treatment conditions that you're looking at. So more than one treatment variable or factor examine multiple independent variables, and one dependent variable. Okay, so I got hopefully, I know I might have jumbled through that, but this picture hopefully makes it a lot more sense. So this is what a simple ANOVA looks like, or one-way ANOVA, or a single factor ANOVA. There's various terms that have been applied to it depending on what you look at and the author you read and the fields of study that you look at. So if we want to look at sanctions for school delinquency to see how they affect grade point averages or graduation rates or whatever. So if you want to look at say sanction is for getting in a fight at school. So we institute a treatment variable, a counseling or whatever. We could do suspension, see that type of effect, and this could be arrested because that's technically it's an assault. Or you could do nothing at all if you wanted to add a fourth factor onto it as well, and that's possible as well. So this is a simple ANOVA. It's just looking at one thing. But three different treatments, three different independent variables, and one dependent variable. The dependent variable would be, graduation rate, or the dependent variable could be grade point average, right? And see how these things have an effect. So it's easy to think about these things and look at these as factorials and factorial designs. When there's more than one treatment variable involved, you can kind of break them down into these little, columns and charts, and using those types of things. So if we want to extend it into a 3x2 factorial design, we can look at the sanctions and continue on counseling, suspension, and jail, and break it down between gender here, right? So that would be 3 levels of treatment, counseling, suspension, and jail. 2 levels of grouping factors, males and females by gender. All right, we can make it and that's a 3x2 factorial design. We can make it 3x4. We could do 9th, 10th, 11th, and 12th grade, right? Or we could add a fourth level of treatment as well, which we could do nothing whatsoever. So we could make it a 4x4. So be 9th, 10th, 11th, and 12th graders, and then these three plus a no treatment at all variable, right? So hopefully that makes sense. And that's kind of what factorial designs look at, and just thinking about these things and how you would, you can model them there, and that should give you a good picture of how these things tend to look. But we're going to really focus on simple ANOVA. Just looking at this right here, like three different independent variables on one dependent variable, and see if they differ significantly, if the means differ significantly. Now, I've said this a few times, and remember before with the t-test, really what statistics is looking at means and variation, like looking at the differences, if the means and the variation together, and if there's significant differences between those, all right? And there's lots of conditional factors that are employed. As far as the ANOVA, the things that you're looking at is the idea of with the t-test, the null hypothesis would be only 2 variables, but with ANOVA, it's 3, perhaps 4, perhaps 5 different levels, okay? That all these means do not significantly differ from one another, right? The research hypothesis would be that there is a significant difference between the means within the sample, within the population, okay, within the data provided. So there is a difference between the mean value of the first independent variable, second independent variable, third independent variable, the first treatment, second treatment, third treatment, counseling, suspension, or jail, right? That would be your research hypothesis. It's not necessarily telling you which one has more of a significant effect. It's more of a holistic test. It looks at everything simultaneously, but that's really what the null is saying, that there is no difference. The research is saying there is a significant difference between one or more of the means within the analysis you conducted. So the F statistic itself looks at the within group variance and the between group variance. So the within group variance should be small, and this is the variance between the people who, if we go back to the example here, who received counseling or suspension or jail, their GPAs or their graduation rate should be like, or if you want to look at their overall, their overall grades, say the folks who received treatment, anger management or whatever, or some counseling, ended up having their overall grade being around a B or an A. All right, those who were suspended ended up getting a C. Those who were placed in jail ended up getting an F. That's, not that treatment variable you saw them getting 20s as well as 90s, right? That's a lot of variation within, but between, hopefully there's significance. Well, ideally there would be significance, a large margin. That's how you achieve significance. I'm not saying that is ideal, is right, good or bad or whatever. Okay, these things should be objective numbers and they're based on factual data and things that shouldn't be manipulated whatsoever. So I'm going to quickly walk through an example that I have here, and I'm looking at a four-factor analysis for time smoked marijuana in the past year. All right, and we looked at high school, 9th, 10th, and 11th, and 12th grade, just to determine if there's a significant difference. Okay, we're going to do a simple analysis of variance, and try to assess whether or not the time smoking marijuana differ from 9th grade to 12th grade based on the students enrolled in a particular high school, right? So we have a sample of 15 here. This is the number of subjects involved. Now our null hypothesis is the number of times individuals smoke marijuana does not differ by grade, where all means are equal. All right. The alternative hypothesis is that the number of times individuals smoke marijuana differs by grade, where at least one of the means is significantly different. That's how you would interpret the alternative hypothesis, okay, for this example here. Now we can work this stuff out by hand. You can do that in your textbook, and it's important to know how to work this stuff out by hand because it's you can understand the means, you can get the variation, you can calculate the variation for each and every factor that we're looking at here, right? And the means for each and every factor as well. But since this is online and we're limited in time here, well, we're just going to use the Excel data analysis tool. So go to the data tab here, data analysis, ANOVA single factor, click on that, click OK. Now our input range, we're going to input all the data, 9th grade and 12th graders and all of it, okay? So we're going to include the labels because I highlight 9th, 10th, 11th, and 12th grade. So that's clicked, that's checked already. And I'm going to place my output. I'm going to place it right here, okay? And then click OK. And then it's going to give you some results here. Now, how you look at these results, you can see the sums. In the 9th grader, there were 15 individuals. The sum, their total number of times smoking marijuana is 36. And I can compute this manually if I wanted to. We've done that before. And we can see the mean. This is the average, the mean, and the total amount of variance between it, okay? So you can see the mean for 9th graders, 10th graders, 11th graders, and 12th graders. So we're looking at if these means essentially are different from one another. That's what the null hypothesis says, that they're not significantly. The alternative says at least one of them does significantly differ, okay, when accounting for all the factors in the model. So this is the variance score. You can calculate the variance as well. And it gives that type of stuff. Now, here's the between group and within group, the total amount of variance that is occurred there, the degrees of freedom. So there's 3. Now I know we talked about degrees of freedom, how it tends to be n-1. So this is between groups, 9th, 10th, and 11th, and 12th grade. So there's 4. 4 minus 1 equals 3, and that's the between group. The within groups, so there's 15 total subjects. So 15 plus 15 plus 15 plus 15, 15, 30, 45, 60, right? And that we know that there's 4 different groups. So 60 minus 4 is the degree of freedom for within groups. Now, we'll look at the F statistic as well right here. So according to this F statistic, it does not exceed the F critical value, all right? If you computed this manually, there's charts in the back of your textbook. It gives you a chart on how to interpret the F statistic and compare it to the F critical value. This one does not exceed the critical value, and then we see that within the probability of it occurring within the population. So this is roughly 72 out of 100 times this value is going to occur. So this is not a significant value, okay? By whatsoever. So those are your results right here, and I have a quick interpretation of the stuff I just said here. So hopefully you can see this. So this is how you would write out your results. This is how you would write them out in a paper, in an article, or whatever. If you did it in ANOVA, you would say that F, these are your degrees of freedom right here. F is the statement that indicates the test was being conducted. Remember last time we've had a T test, a T here because we did a T test, but here it's an F test because it's ANOVA. It's associated with Fisher. The degrees of freedom, 3 for the number of between groups, 56 for the number of within groups, and then the obtained value. So this is your F value. It's 0.04469, and that the p-value exceeds 0.05. Okay, it exceeds the critical. F does not exceed the critical value. So how will we interpret these things? How will we interpret the results that were achieved here? Would say that the F statistic value of 0.045 does not exceed the F critical value. And so I included this. I included this statement here. And this is perhaps a good way and a good idea and a good way if you're writing a dissertation or a thesis or a journal article or even in a stats class. So include that within the statement. The F statistic value of 0.45 does not exceed the F critical value. Therefore, you failed to reject the null hypothesis. Include that there is not a significant difference between the mean values of marijuana use based on high school grade. So, you know, it's not a significant value, and that's fine. It doesn't have to be. People, you know, get worked up thinking that the values have to be significant. All your job is to interpret the data, right? This is a manufactured data set anyway, so it doesn't necessarily matter. But from a statistical standpoint, if you look at the means, you can say, well, wow, this looks, only in 9th grade, only the average use is 2.4 when the 12th grade is 4.7. Perhaps it differs between all grade levels. Well, statistically, no, all right? And we could have just reported the averages and left it misleading. But people want to take it a step further and understand, is it significantly different, or is it perhaps due to some chance? And as we see from our F value, from this test here, it is perhaps due to chance, all right, that this value, and it doesn't necessarily mean anything significantly. Although interesting, not necessarily significant, all right? And that's the same way with t-test as well, all right? You might not get a significant value, you might not achieve a significant value between the mean because the variation in all the factors that are calculated and come together within the test itself doesn't indicate a significant value, and that's perfectly fine. If it was significant, how will we interpret it? Let's just say, for example, if it was a significant value and it did exceed the F critical value, we would reject. And instead of fail to reject the null hypothesis, we would reject the null hypothesis and conclude that there is a significant difference between the means of marijuana use based on high school grade, right? And that's really all you can do and all you can say within it. You can't say that 9th graders are using it less than 12th graders. You just know that there's a significant difference within this test. We could do a t-test to extend that, right? We could actually do a t-test to see if 9th graders did significantly differ from 12th graders. How will we do that? We could go back to our t-test. We could go back and do a what is the t-test? T-test for assuming equal variances here, right? And then let's go. Let's delete this stuff. I know I'm going a little beyond the scope of what today, but it's good to reiterate stuff we've done in the past. So we're going to just do a t-test to determine if the means differ between 9th and 12th graders here. All right, so we include the labels and we'll put the output right below it, okay? So this is a t-test. Here, you could go back and look at the previous thing, but we understand that the p-values are not significant. They are not less than 0.05 here, based on the t-value and the p-critical value. Even if we looked at a one-tailed test, right, a directional test saying that seniors use marijuana at a much higher rate than freshmen do. But this is only 15 out of 100 times, and our threshold is generally 0.05 within the social sciences. So hopefully this stuff helps out, and hopefully it's beneficial to y'all and get y'all going on ANOVAs and kind of looking at these things. So, good luck to y'all, and take care.